Hello everyone. This video will cover the topic of operating system performance tuning. We will explore optimization techniques and performance analysis methods to ensure your system runs efficiently and smoothly. Operating system performance tuning is the process of optimizing your system to achieve the best possible performance. The key objectives include optimizing resource utilization, which means making the most efficient use of your system's hardware. Minimizing response time, which ensures that applications and processes start and run quickly. Maximizing throughput, which allows your system to handle a large amount of work efficiently. Reducing system bottlenecks, which identifies and removes obstacles that slow down the system. Balancing workload across system components, which distributes tasks evenly to prevent any single component from being overloaded. Key performance metrics to consider include CPU utilization, which measures how much the central processing unit is being used. Memory usage and paging, which monitors how memory is being used and whether the system is relying too much on slower disk storage. Disk input-output operations, which measures how quickly data is being read from and written to the disk. Network throughput, which measures the speed of data transfer over the network. Process scheduling efficiency, which assesses how efficiently tasks are being managed by the operating system. Let's discuss Central Processing Unit, or CPU optimization techniques. Process scheduling strategies involve optimizing the CPU scheduler to significantly improve system performance. Implement priority-based scheduling for critical processes to ensure they get the CPU time they need. Adjust time slice durations, which is the amount of time each process gets to run, for better responsiveness. Use CPU affinity to bind processes to specific cores to optimize cache usage. Set nice values to control process priorities and ensure important tasks are not starved of resources. As an example, in Linux, to view current process priorities, use the command ps-eopid nipri-com. To set process priority, also known as nice value, use the command renice-10-p process ID. Here, process ID should be replaced with the actual process ID. To set CPU affinity for a process, use the command taskset-pc0,1 process ID with the actual process ID. This command assigns the process to cores 0 and 1. Now let's explore memory optimization techniques. Memory management strategies include configuring swap space, which is disk space used as virtual memory, to handle situations when physical memory is full. Tune the page cache, which is memory used to cache disk data, to improve input-output performance. Set memory limits for processes to prevent them from using too much memory and causing system instability. Use huge pages for large memory allocations to reduce overhead. Configure the out-of-memory, also known as OOM killer, which is a process that the kernel uses to kill processes when the system is critically low on memory. As an example, to check memory usage in Linux, you can use the command free-h. To set swappiness, which controls how aggressively the system uses swap space, you can use the command sysctlvm. Swappiness equals 10. The swappiness value can range from 0 to 100. To enable huge pages, use the command echo 20 greater than sign /proc/sys/vim/nr_huge pages. This command allocates 20 huge pages. To set a process memory limit, use the command ulimit-v83888608, which sets the limit to 8 GB. Now let's focus on disk input-output or I/O optimization techniques. One crucial aspect is optimizing the input-output scheduler. Choose the appropriate scheduler based on your workload. Completely Fair Queuing, or CFQ, is a good general-purpose scheduler. The deadline scheduler is suitable for latency-sensitive workloads. The No Operation, or NOOP, scheduler is best for solid-state drives or SSDs. Budget Fair Queuing, or BFQ, is designed for desktop systems. You can also set input-output priorities for critical processes to ensure they get preferential access to disk resources. As an example, to check the current input-output scheduler, use the command cat/sys/block/SDA/Q/scheduler. To change the input-output scheduler, use the command echo bfq greater than sign/sys/block/SDA/Q/scheduler. To set the read-ahead buffer size, which determines how much data is read in advance, use the command blockdev_cetra 4096 /dev/SDA. To set input-output priority for a process, use the command ionice-c2-n0-p1234 with the actual process ID. This command sets the input-output priority of process 1234 to class 2, best effort with priority 0. Now let's explore network optimization techniques. A key area is optimizing the Transmission Control Protocol/Internet Protocol, or TCP/IP stack. This includes several strategies. Use Transmission Control Protocol or TCP window scaling to increase buffer sizes for high-bandwidth networks, which improves throughput. Select the appropriate congestion control algorithm such as bottleneck bandwidth and round-trip propagation time, or BBR, Cubic or Westwood Plus, based on different network conditions. Tune socket buffers to optimize send and receive buffers for better throughput. As an example, to increase TCP window size, use the commands sysctl-wnet.core.rmem_max equals 167777216 and sysctl-wnet core mem_max equals 167777216. To set the TCP congestion control algorithm, use the command sysctl-wnet IPv4 TCP_congestion_control equals BBR. To enable TCP fast open, use the command sysctl-wnet IPv4 TCP_fast open equals 3. To increase the connection backlog, which is the number of pending connections, use the command sysctl-wnet.core, so maxkin equals 4096. To effectively tune operating system performance, it's essential to use the right monitoring tools. Several system monitoring tools are available. Top provides real-time process monitoring and system statistics, allowing you to see CPU, memory, and process usage. VMstat, which stands for Virtual Memory Statistics, provides virtual memory statistics and block input-output information, helping you identify memory-related bottlenecks. IOStat provides CPU and disk input-output statistics, helping you analyze disk performance. NetStat, or SS, provides network connections and statistics, allowing you to monitor network traffic. SAR, which stands for System Activity Reporter, collects system activity data for historical analysis. Perf enables performance analysis with CPU profiling, helping you identify performance bottlenecks in your code. As an example, to monitor CPU and memory usage, use the command top-b-n1. To get disk input-output statistics, use the command iostat-xc1. For network statistics, use the command ss-tone. For process profiling, use perf record-f99-p process ID-g-sleep30, followed by perf report, replacing process ID with the actual process ID. To trace system calls, use the command strace-p process ID, again replacing process ID with the actual process ID. Benchmarking is a critical step in assessing system performance and the impact of tuning efforts. Several benchmarking tools are available. Sysbench is a versatile tool for benchmarking CPU, memory, disk input-output, and more. Bonnie++ is used for disk input-output benchmarking. FIO, which stands for Flexible Input-Output Tester, is another tool for disk input-output benchmarking. perf3 is used for network performance testing. The basic benchmarking process involves establishing a baseline performance by running benchmarks before making any changes. Then apply system optimizations, such as tuning kernel parameters or updating system configurations. Next, rerun the benchmarks to measure the impact of the optimizations. Finally, compare and analyze the results to determine whether the changes have improved performance. As an example, to run a central processing unit or CPU benchmark with sysbench, use the command sysbench CPU double-CPU max-prime equals 20,000 run. To run a memory benchmark, use the command sysbench memory double-memory-block-size equals 1K double-memory-total-size equals 10G run. To run a disk input-output benchmark with FIO, use the command FIO double-name equals random-write double-IO engine equals POSIXAO double-RW equals randwrite double-BS equals 4K double-size equals 4G. Kernel parameter tuning involves modifying settings that control the behavior of the Linux kernel, which can significantly impact system performance. Key kernel parameters include vm.swappiness, which controls how aggressively memory pages are swapped to disk. Lower values reduce swapping, which can improve performance if you have enough random access memory, or RAM. vm.dirty_ratio determines the percentage of memory that can be filled with dirty pages before processes start writing data to disk. Increasing this value can improve write performance. Kernel.sched_migration_cost_ns controls process migration between central processing units, or CPUs. Adjusting this value can reduce overhead. fs.file-max sets the maximum number of file handles the kernel can allocate. Increasing this value can prevent file handle exhaustion. net.core.somaxcan sets the maximum socket connection backlog, which is the number of pending connections. Increasing this value can help with high-traffic servers. Kernel.schmax sets the maximum size of a shared memory segment. Increasing this can benefit applications that use shared memory. As an example, to view current kernel parameters, use the command sysctl-a-pipegrep vm.swappiness. To temporarily change a parameter, use the command sysctl-wvm.swappiness equals 10. To make a permanent change, add the line vm.swappiness equals 10 to the file /etc/sysctl.onf, and then run the command sysctl-p. To increase the file descriptors limit, add the line fs.file-max equals 2097152 to /etc/sysctl.onf. To achieve the best results with operating system performance tuning, it's essential to follow certain best practices. Establish performance baselines by measuring performance before making changes to understand their impact. Implement incremental changes, making one change at a time and measuring its effect. This approach helps isolate the impact of each optimization. Focus on workload-specific tuning, optimizing for your specific use case rather than generic scenarios. Document all changes, keeping detailed records of optimizations and their effects for future reference. In summary, performance tuning is an iterative process. Focus on the bottleneck with the highest impact. Measure before and after each optimization to quantify the improvements. Balance resource utilization across subsystems to avoid creating new bottlenecks. Consider workload patterns when optimizing to ensure the changes are beneficial for your specific applications. Finally, test in environments similar to production to ensure the optimizations work as expected in real-world conditions. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.